let's get started. Hi, everyone. Welcome to lecture 8. Today, we'll talk about different CNN architectures. So we had an introduction to convolutional neural network previous lectures. So today, we'll talk about different architectures and how things are evolving. Okay, so before we go into details, as always, reminder, project 1 is due tonight. If you haven't submitted on AutoGrader, you should consider doing it immediately. And AutoGrader, you don't have to have like everything done. It allows you to submit partially as well. I should have mentioned that before. So for the next project, try to iteratively check what's happening with AutoGrader and don't wait till the end. So even if you have like 2 things that you implemented, submit and see what happens, right? Yeah, so it's due today. If you have any questions, please post it on EdSTEM. And if others who have completed it, maybe you can check EdSTEM and try to answer those posts. I'm traveling after this, I'm flying, so I won't be able to answer as frequently as I can. So please help the other folks by answering questions on EdSTEM. Yeah? Yes, Miles.
Your grades just like update with the AutoGrader grade, like I did this. How does it work?
I will fetch from the AutoGrader at the end, which would be our final summation numbers, and then put it on the canvas or grade school, whatever. Cool. Okay. So project 2 will be up tonight, and it'll be due on Tuesday, February 21st. So this will be like short window. So I would say like get started and try to use AutoGrader, and AutoGrader will be like up by Monday. So you can start submitting from then. Yeah. Okay. Cool. So a little bit of a recap from previous lectures. So we talked about these components in convolutional neural networks. So we talked about having fully connected layers, activation functions like ReLU functions, and convolution layers, pooling layers. And then we got to a point where we're going to talk about normalization, so which we'll continue right now. Okay, so basically, the intuition behind having normalization is that the input to a particular layer, if it is bounded, if it has some characteristics, it is easy for your optimization to converge. If you have deeper and deeper networks, the training becomes really hard. So you got to have some sort of control over your input values for each layer to keep it attractable. Okay, so the thing that happens common if you don't do normalization is the fact that your inputs are not centered, like centered around 0. And they might have different scaling per element, which could like throw off your optimization routine, which means your gradients are going to be like super hard to compute and keep your training in control. So the idea is to basically force this input values to be within some bounds or have some characteristics. So common approach here is to use a 0 mean with unit variance. So as you might be familiar here, so if X is the actual output from the previous layer, which you would actually use as an input, we want to modify that and center that around 0 with a unit variance. And this is also a differentiable function, so you can actually add this to your computational graph, and your backpropagation is going to be automatic. Yeah. And why are we calling this batch normalization? Is because if you're using a batch of inputs for your training, you want to normalize that in a particular fashion. So batch normalization is done in the dimension of the number of batches. For instance, here, if the dimension of the input is n cross d, you are normalizing across the dimension of n. Yeah. So you compute the mean, you compute the variance, and then you have maybe not. So, so then you compute this x hat from using the mean and the variance that you computed. And you also had this small value for numerical stability. The thing to note here is the shape of these values. So for instance, mean, it's going to be a shape of B because we're talking about normalizing over N. Same thing for the variance or standard deviation. And for the output that you get after your batch normalization, it has to be the same as the input. Right? We are just changing the values or like trying to scale the values here. So the problem here is that this might seem like too much of a constraint that we are inducing into, let's say, a deep neural network, right? So having a constraint over every layer to be within zero Gaussian is probably too much of a constraint. So one thing that people have come up with is to add a learning parameters and say, okay, I'm going to get these values, but then I'm going to use two values like gamma and beta to actually make them a little bit flexible. You're not constraining them to be absolutely zero mean and variance. You're giving them a little bit of wiggle room that you can learn over the training phase. So you're introducing two different learning parameters, gamma and beta. The thing to note is that that actually makes it like a linear function again, right? One other thing to note is you want to think about it both from the training point of view and testing point of view. During the training, especially when you're using SGD, let's say, you have a mini batch, and whenever you're computing this mean and variance, you're computing for that mini batch. Whereas during the testing time, you don't want to do that because you don't want to accumulate or look at two different test samples and normalize across them. Like they have to be considered independently. Like for instance, let's say in your testing scenario, you had an apple and an orange. You don't want to compute a mean between those values because that doesn't make sense while you're trying to classify them. Does it? So during the training, it's okay to do that because you're considering everything in a batch, whereas in testing, you want them to be done independently. So the trick that you can follow here is to actually have a running average for the mean and the variance during your training, and then use those values in the testing time as a constant. So it's not going to depend on the test batches, but it'll be like based off of the values that came out of the training. Does it make sense? So during the testing, you are normalizing over the batch. Sorry, during the training, you're doing over the batch, whereas during the testing, you don't want to do that. That's the whole point. But you need to anyways use them during the testing. The way to compute that is to have a running average during the training phase. And once you have that, you have these two constant values that you can plug in when you are doing testing. So here is sort of pseudo code here. So you can have mu during testing to be 0. And then during the training, you are kind of updating the new value. This is what I meant by running average. Yes.
What is the point of batch normalization? I mean, does it have any effect while training?
So batch normalization is super useful, and we have seen that it works really, really well when you have many layers in your neural network. The caveat is nobody knows why it is effective. It's theoretically not super proven that this is why batch normalization is helpful. There is definitely an intuition behind doing that over layers, but why does it actually work? We do not know, but it works very well. That's the kind of, I mean, if you look at it mostly in deep learning, that sort of is what happens. Like if you don't know, you try a bunch of things, and sometimes it's not like easy to explain why that works. And this is one of the cases. So I will see, like when we talk about the history of CNN architectures, you will see at a point when we started introducing batch normalization, we had a huge revolution in the in terms of accuracy numbers and what people were able to do when they're constructing network architectures. Any questions so far? Okay. So one other thing to note here is the fact that so like I said, the batch norm at the end becomes a linear operator, which means during the inference time, you can sort of use this operation into the previous network, and it would not have an additional computational effect on during the inference time. So it's something that is effective and improves your inference time computationally. Okay, so let's look at some examples of how batch normalization happens on convolutional neural networks. So the thing on your left side is, let's say the input is just batch cross the dimensions of your input. Whereas on the right side, we're talking about CNNs. We're talking about convolutional neural networks. So here the input is you have the batch number n, and then you have the depth of the input channel and the spatial resolution, which is h cross w. So here, when you normalize, your normalization looks like this because you're normalizing not only across n, but you're doing the normalization on the spatial inputs as well. So let's see how or where do you actually plug in the batch normalization. This actually happens after your activation function. So you have your fully connected layer followed by activation function. Oh, actually, I think it's the other way around. So yeah, so you do batch normalization and then you apply activation function. Danish is the activation function here. And let's see some of the features of using batch normalization. So this makes deep networks to be easily trainable. Once you have, let's say, beyond 10 layers, 10 convolutional layers or fully connected layers, we'll see that when we look at the architectures. It allows for you to use higher learning rates at the very beginning, which means you can converge faster. It also becomes robust to initialization because you're normalizing at every layer. So even if your input fluctuates quite a lot, you are robust to that. And the batch normalization also gives this additional characteristics of being noisy because of those two parameters that we saw, which are like learn parameters. It also acts as a regularization that we saw earlier in the previous lectures. If you remember, like regularization is being used to not overfit to your training data. And like I said earlier, because of the linear operation with those two learn parameters, this is actually a zero overhead at the test time. You're not thinking about those two parameters, which can be fused to a previous layer. It's more of an implementation detail, but this is useful when you have batch normalization. Okay, so some plotting here that kind of explains why batch normalization is very prevalent. So if you look at this dotted line here, which was how the accuracy was before batch normalization was used. So this was like, we will see the this inception, this from GoogleNet, which did not use batch normalization. This is the accuracy over the training iterations. But when you start using batch normalization, you can see that it kind of converges really, really faster. And the other ones are basically saying how many times you used batch normalization in your network. So yeah, so in general, this is something that you'll see in all the modern networks. Okay. So like I said earlier, it's not well understood theoretically. And also, like if you have too much variation in your data, it so happens that it is super hard to figure out why the behavior is different from training and to testing. This is common source of bug that people have indicated during like using batch normalization for training and testing. Something to watch out for, but like once you figure this out, it is very effective and you'll get like better accuracies. One other normalization that you'll often see is layer normalization. This was introduced because of the discrepancy that we had between the training and testing. So like I said, during the testing time, you don't want to normalize over the batch because you want to consider each of the samples independent of each other. You don't want to compute something like a mean and variance, which would affect your accuracy. Layer normalization, on the other hand, kind of tries to solve that problem. So you're normalizing not over the batch, but you're normalizing over the dimension of the input. Now they are still being considered independently during the testing time. So there is no discrepancy between the training and testing. Is that clear? So earlier, batch normalization is doing normalization over the batch dimension. Here, we are doing it over the dimension of the input. Yeah, so this will be like commonly seen in RNNs and transformers, which we'll talk about in the next lectures. So there is also another normalization that you'll probably hear when you're looking at how normalization has been done over the period of time is instance normalization. I would say it's easier to look at it with these plots. So batch normalization happens on the dimension of n, right? So all of these have same inputs. So it's n cross c cross h cross w. Batch normalization happens on the batch dimension. The layer normalization happens on the depth of your inputs, whereas the instant actually happens for every particular cell or the pixel in your image separately. You can also do something called group normalization, which actually splits your input into multiple groups on the dimension, on the input dimension or the depth dimension, and tries to do the normalization. There are some benefits to this, but most often you will see batch normalization and layer normalization in the network architectures. Any questions so far? Okay. So we saw different components of convolutional neural networks earlier, but we did not talk about how to put them together, right? We saw LeNet, which was like a classical network for document recognition in the previous lecture. We talked about how they did, but we didn't talk about like how we should be looking to do this for a new CNN architectures. Okay, so I think a good way to think about this is to ground this on the accuracies that these network architects have been able to get on ImageNet classification. So far you're seeing two works, 2010 and 2011, and they did not use deep learning yet. So in 2012, the AlexNet came into picture, which started using neural networks, and they have 8 layers. And you can see that they had a higher accuracy rate, which means the error dropped from 25.8 to 16.4. This was a huge achievement, especially with the advent of deep neural networks. Okay, so let's look at what AlexNet architecture is and how they have chained these components to achieve this particular accuracy. Okay. So AlexNet is again like it's a seminal paper in the field, and it has huge impact not only in the computer science community but also other communities who use machine learning. We'll see that in a bit, but in essence, it has, let's say, 227 cross 227 inputs. It has 5 convolution layers. It has max pooling between the convolution layers, and 3 fully connected layers, and ReLU as the nonlinearity function. So that's the overall gist of what the AlexNet actually has. They also use something called local response normalization, and they did not use batch normalization. Batch normalization comes like later, like 2015 or so. Which is not used anymore. So we'll not go into that. And the thing to note here is back in the day, like AlexNet, which looks really small with 8 layers, were actually put on 2 different GPUs. And the model itself was split into 2 different GPUs. So when a forward pass was happening, it has to be happened one after the other. So that was the case. So, and there is a little bit of discrepancy. I think the network architecture, which is also kind of unique in the way how they put it in the papers, it's like cut for some reason. And I don't know, I think it's referred like that everywhere else as well. So there is a little bit of discrepancy between the numbers that we'll talk today in the lecture versus the architecture, but they are close. Like for instance, the input here in the figure is 224 cross 224, but we'll use 227 cross 227. Like, but it's very, very, very close. Okay, so to give a little bit of understanding of how huge of an impact this particular work has made, let's look at the number of citations. So citations is one way to kind of see how much impact a particular work has made over the years. So again, this was like published in 2013. And it's almost like a decade. So we have over 120,000 citations. And to kind of give like, okay, what is a good number here? We are trying to see some seminal works in other spaces or some very well-known works in the field of science. So Darwin's paper, which came out in 1859, has 60,000 citations. And Shannon's theory of communication, which came out in 1948, has 140,000 citations. So well, AlexNet is getting closer. And then the other ones on molecular structure, which was published in 1953, has 16,000 citations. So again, citation is not the only way to kind of like compare different works, but this gives you like an understanding of how huge of an impact this particular work had. Especially like this is 2023, right? It's been a 1 month, and they already had like 1,400 citations. So anyway, so yeah, this is a huge thing, and the authors like Jeff Hinton is one of the Turing Award winners in the field. Okay, and now getting into numbers. Okay, so we saw in the previous lecture how to compute output size, right? So AlexNet in the first convolution layer, the input is 3-channeled RGB image with height and width of 227. And the first layer uses 64 filters, where each filter again has 3 as the channel, and the kernel size of 11 cross 11, stride of 4, and padding of 2. Can somebody tell what is the output channel number would be? The channel, just 64, right? 64 cross something that we can compute with this particular formula that we saw earlier, right? Now, can you think about like what is the memory that this particular layer would have to use up? What do you want to store for this particular layer, or the output of this particular layer? Sorry? Floating point weights of the weight, or the activation maps? So it's actually the activation maps. You want to store the output. So number of output elements at the end of this operation is what you want to store in the memory, and so that it can be used for the next layer. So it's the output is 64, and the output resolution is 56 cross 56. So that's the amount. And you're using 32-bit floating point list. So if you're multiplying with that, and again, this is for kilobytes, it's 784 kilobytes. Yeah. So think, remember, when you're computing memory, you're talking about output. Okay, what are the parameters? Learning parameters, not the hyper learning parameters. We talked about this in the previous lecture. Yes, because now we are talking about the weight shape or the filters. So 64 is the number of filters, and each filter has 3 cross 11 cross 11 as a size, because that is what you're using to do the inner product. And of course, like we should not forget the bias as well. So you want to add bias, like which is the number of filters that you are using. For the later discussions, we might like ignore the bias because it's quite small in number, less significant as opposed to the weight shape. But yeah, but you need to consider bias shape when you're computing parameters. Okay, so how many flops will be used for this particular convolutional layer operation? We discussed that as well in the previous lecture. What do you need to think about when you're computing the output, right? Output, and you want to think about like for each value in your output, what was the operation that went into it to compute that? It's basically an inner product that you had. So if you're computing flops, this is the output number of elements multiplied by the filter size, which is 3 cross 11 cross 11. Good. Okay, so we talked about memory, we talked about parameters, we talked about flops. For memory, you want to use the activation maps, which is basically output, and multiply that with bytes. Whereas for parameters, you're going to use the weights and biases, especially for convolution layer, it's the size of your kernels, like of all the filters together. For computing the flops, you are again using the output elements and look at like what each element in the output has to, what operations are being performed to compute each element in the output. And here we are specifically using multiply and add together because from the hardware point of view, both of those operations can be done with the same time. Yeah. Okay. So the next layer is a pooling layer. So again, the output from the first convolutional operation is 64 channels with H and W being 56 and 56. So that is what is your input as well. And AlexNet uses a kernel size of 3 with stride of 2, no padding for the max pooling. What do you think is the output size? This is slightly trickier than what we saw in the previous lecture. So in the previous lecture, we saw if there was so 4 cross 4 with a kernel, let's say 2 by 2. So this was when you put the kernel with a stride 2, the next stride will be here. So the output of the entire operation would be 2 by 2, right? When you're doing max pooling. Whereas here it is slightly different. It has 3 as the kernel size, with stride being 2. So there's an overlap. Here in this particular case, there is no overlap, whereas the one that you're seeing on the slide, there's no overlap. Okay, so there is an easy way to compute that. Like you can just look at what is the size of the input minus the size of the kernel size, divide by the stride and plus 1. And in this particular case, for some reason, they chose these numbers, which gives you a floating point, and then you have to like kind of adjust that to get your output size. So they're doing the flooring here. Okay, but the thing to remember is the pooling operation does not have any learning parameters. And before that, okay, so let's see what is the memory that goes into it. So again, we are looking at the output number of output elements. So here is C out multiplied by H dash and W dash, and 4 bytes per element. Similar to what we saw earlier, you can compute the memory. For the parameters, pooling layers do not have any parameters. That we saw that in the previous lecture. Yeah, something to remember by. So pooling, there is no learning parameters involved. And for the flops, it's actually negligible here. We are talking about millions of flops here. But again, you have to consider your outputs and what operation went into to actually calculate each of the element in your output. Yeah. And it's just like listed out as 0, but it's actually 0.4 million flops. Okay. So I think it'll be a good exercise. If you guys want to sit and like try to write this out. So you understand how the memory is computed, how the parameters are considered, and how many flops goes into goes into the operation for doing each of these layers. Any questions so far before we move to flattening? Okay. Yes.
So the memory here doesn't really consider the backward process. And usually backward process or like the backward propagation also increases memory. Is that usually never considered when thinking of like how the model?
That's a good question. I think one of the reasons for that could be it's just that it's the same operation being done twice. So when you're comparing different architectures, you probably don't need to think about backward pass. But I'm not entirely sure. Okay. So they do perform a flattening operation after the pool 5. So flattening is basically taking out your matrix and giving a vector. If you think about it, again, the memory is being used up as much as the output values are, right? So that's why you have the same value as the previous one. And after the flattening operation, there is a fully connected neural network or fully connected layer. So we know that fully connected layer is basically WX plus B, or weight matrix multiplied by the input plus the bias. So here's the number of parameters for that. And the flops is basically the number of operations or the number of inner products that you do in your fully connected layer. Yeah. Okay. So again, it's a good practice go over, especially given AlexNet is like only using 8 layers to understand the nuts and bolts of like what is the memory, what are the parameters, and how much flops are we talking about? Okay, so I think at this point, the way they kind of came up with this was basically trial and error. And obviously, it would have taken like a lot of time for them to figure this out, to come up with this architecture that kind of works and also beats the previous approaches in the ImageNet. But one thing that we could probably take away from this table is the trends on the memory and parameters and flops or the layers of the AlexNet. So if you think about it, let's just look at the memory here. So memory early on, when you're using, when you're starting from the first convolution, is super high. When you come to the fully connected networks, it's really low. That's because over the period of time, your outputs are getting lesser and lesser. You're like trying to reduce the dimensions of your inputs. If you look at the parameters on the other hand is increasing, and it's too high when it starts coming to the fully connected layers. So if you think about it, parameters are basically the filter sizes, right? And initially, the filter sizes are basically determined by your designer, of course. Like, so for instance, you see that convolution 2 has a higher number of parameters, but the bigger difference is like between the convolution layer and the fully connected layer. Convolution layer only has the parameters to be the filter size, whereas for the fully connected neural network, it depends on the input size and the output size as well. So we are talking about W and bias. Is that clear? So at this point, we are trying to convert 9,216 values to 4,096 values. So for that, you kind of need a weight matrix, which is larger in number. Yeah. Okay. So again, in terms of flops or computation, you can see that convolution layers take more as opposed to the fully connected layers. That's because you're doing the inner product operation over the entire input size, as opposed to fully connected neural network where it's just a linear operation followed by array loop. Yeah. Okay. Now let's kind of summarize this. So if you're looking at memory, the convolution layers take more memory, especially for this particular architecture. If you're looking at the parameters, again, the parameter shoots up when you start looking at fully connected layers. And in terms of floating point operations, convolution layers take more than the fully connected layers. So this is interesting to kind of note, because in the next set of architectures, we'll see how they are differing from this, how they are trying to improve and how they are trying to differ from this. Okay. So we looked at AlexNet, the structure, and some characteristics on the memory, parameters, and floating point operations, right? So this is the performance, right, that we saw earlier. And in the next year, there was a different architecture that was proposed, which had same number of layers, but there was an improvement in the accuracy. So the error dropped from 16.4 to 11.7. Carl.
Said Alex that had to be spread over 2 GPUs that were like 2 gigabytes of memory.
Right.
And that memory calculation we just did was like a couple of megabytes. So why did it need 2 GPUs? Oh, wait, maybe I think I'm calculating, but I might need to think a little harder about how much.
Actually, I think there are numbers in the next slide as well. So let's wait for that. Yeah, I cannot think of that on top of my head. I think batch size could have determined as well, but yeah, that's a good observation.
Yeah, I do think that's only a few megabytes.
Yeah. I think it could be considering the batch size that gives you the performance. So this is on the ImageNet data set that we are talking about, which is actually quite significantly bigger in size. So I think that could have been the reason. But yeah, let's look at other slides and see if you find the answer for this. Okay, so there was another layer that was another network architecture that was proposed with same number of layers. It had improvement over the AlexNet. The only thing that they did was retain the same structure, but change the size of the filter. For instance, in the first convolution layer, they changed from 11 cross 11 with stride 4 to 7 cross 7 stride 2. So this basically does not downsample as much as what the AlexNet was doing, right? So this is making it a little deeper. You have much more receptive field as opposed to what you had in the AlexNet. And similarly, in the later layers, like 3 and 4, 3, 4, and 5, they have like large number of filters. So essentially, this is a bigger network than AlexNet. So what we understand at this point is if you have a bigger network, it has better accuracy. And again, like with more filters, your receptive fields increase. So that also helps in understanding the observations of the input better than the earlier work. Apart from that, there is no significant difference between AlexNet and this particular network. Same number of layers, just that they made the network bigger.
Sorry, with more filters, the receptive fields increases?
Yes. So if you think about it earlier in the previous lecture, if you have one convolutional layer added, your receptive field increases by k minus 1. So if you have more
Even added layers, just added the channel dimension of data.
yeah, but we also like decrease the filter size as well. Right, instead of like having 11 cross 11 with stride 4, you're having 7 cross 7 with stride 2, that increases the receptive field. Right? So you can just imagine that like deeper networks have better receptive fields. That is one way to think about it.
Right. This is not deeper, it has the same structure as all.
So deeper in the sense like with more number of filters per convolution layer.
So it's wider.
It's deeper. It's not wider. We are not changing the resolution of the layer, like the spatial resolution of the layer. Instead of having, let's say, 384 layers, we're increasing that to 512 layers. You are increasing the resolution of the output or the activation map, which means you're increasing the more memory, more parameters, better accuracy. So more parameters meaning bigger network. Oh, sorry, bigger network, not deeper network. So I should have like clarified, like bigger network, not deeper.
They call that like a wider network, like wider is not same depth with the things.
No. So I think wider is basically on the dimension of the spatial dimensions. You wanna make that bigger that way. Okay, cool. So I think in 2014, there was a huge jump where a new network, VGG network, came into picture, which had 19 layers, which is almost double the size of what AlexNet and the ZFNet had. And one thing to note here is this was done in academic lab, just with, so the authors of this paper is just a student and an advisor. It's very commendable because they kind of invested in having a bigger network with a lot of computation to actually beat and get a significant improvement in terms of performance, as opposed to what we'll see later on, where the industry is coming into play with a lot of infrastructure. Okay, so what did VGG do? So they came up with design rules that the community can actually build on top of. So earlier, the only thing that we could talk about was like, if you make your network bigger, the accuracy will be good. So that's what we saw between AlexNet and the follow-up work. Whereas with VGG, they also came up with design rules. They gave reasons of why these design choices are better. And they also experimented with networks with different number of layers. So we are talking about 16 and 19 here, but they also had like other 3 variants in their paper. Okay, so what are these design rules? They are basically of 2 folds. One is all the convolution layers should have 3 cross 3 as their size with stride 1 and padding 1. And they talk about why this is better than having, let's say, 5 cross 5. And mostly the design choices of the architecture is basically has 5 stages. So initial 3 stages will have conv layer followed by conv layer, and then followed by a pooling. And the later layers will have either 3 convolution layers or 4 convolution layers followed by pooling. So you might not be able to relate that with the diagram here. I think it's missing one or two layers, but the formula is basically that. So you have 5 convolution stages, with the first 3 being 2 convolution followed by pooling, and the later with 3 or 4 followed by pooling. Okay, so to talk about the first design choice, let's consider a convolution layer which has 5 cross 5 as its size of the filter. So let's say for simplicity, we are considering input to be C and output to be C, which means the input X has the depth of C, and the output after the convolution is also C. So C out and C in are basically C. Can you tell me like what is the number of parameters that this particular layer convolution operation will take? 25 C square, right? And the flops is basically 25 C multiplied by CHW, right? CHW is the output. And 25 C is your, 25 C is the size of your filter. Yeah, so we saw how to compute flops and params. Is that clear? So the reason they say that we can stick to 3 cross 3 is you can have 2 3 cross 3s, which would have the same receptive field as having a single 5 cross 5. So if you imagine adding another layer would increase your receptive field by k minus 1, right? So in the first option, there is only 1 layer. So the receptive field is 5 or 5 cross 5. Whereas in the option 2, we have 2 convolution layers, 3 cross 3 followed by 3 cross 3, which means you are having 3 plus 3 minus 1. So you end up with the same receptive field. Now, if you look at parameters here, this is 19C cross 19C. So, 19C cross 2C. So it is 18C square. And the flops is 18C square HW. Is that clear? Yeah. How did we come up with that number? Sorry, 9. Yeah. So if you compare option 1 with option 2, we are decreasing the number of parameters, and also the computation is being decreased, right, significantly. And the other thing is you can also add a ReLU between the convolution layers, which means you're increasing the nonlinearity of the network, which is good. Yeah. So the 2 3x3 convolution has the same receptive field, and it has fewer parameters, and which means less computation. So that is one design choice that they kind of took and also explained for the community to follow. The other one is like to look at what happens if you use max pool with stride 2 cross 2, with size 2 cross 2 and stride 2. And after every pooling, you can double up the number of filters in your convolution layer. So let's look at like a couple of cases. So let's say you had the in the previous layer you had C as your input depth, and 2h cross 2w to be the size of your input. Let's say the layer here is 3 cross 3. Again, input and output is the same as C. The memory here will be 4 HWC, and the parameters is 9C square, and the flops is 36 HWC square. So this is the previous layer. Now, if you follow their design choice of doing a max pool of size 2 cross 2 with stride 2, you are basically reducing the size of the resolution, right? So it was earlier 2h cross 2w. Now that is being reduced to h cross w here. And if you're doubling the number of channels, you can have like the input to be 2c. So this is happening in the next stage. Now, if you use the same convolution operator, 3 cross 3, and have the same input and output, which is 2c and 2c, you can see that the memory params and flops are similar to what you had in the first layer. So by taking the design choice of like after a convolution layer, we are doing a max pooling with 2 cross 2 as a filter size, followed by 2 stride, and doubling the channels for the next convolution layer. You're keeping both of these layers computation to be same. So if you look at the architecture, this is what is happening. We had 64 filters here, followed by pooling, and then you double up the number of filters to 128. And you keep doing that over the network architecture. So the conclusion of this particular design choice is that the convolution layers at each spatial resolution take the same amount of computation. So you are trying to control the number of computation over the layers. So to just compare the memory params and mflops between AlexNet and VGG, VGG is actually huge in terms of the number of parameters as well as the memory and also the computation. So you can hardly see the bars on the AlexNet, right? So along with the idea of like, if you have bigger neural networks with larger number of parameters, your accuracy is going to be better. At the same time, what VGG was able to do was give you these design choices that would help you in constructing your own architectures. So the trend of having bigger networks will give bigger accuracy is still holds, but they also give you design choices that you are able to understand much more detail. Yeah. And any guesses on why is it called VGG? This is from a research group. The name is Visual Geometry Group. They kind of added that to their name of the network. Okay, so if you want to go a little bit details here. So for instance, if you look at the memory, VGG 16 specifically has almost 25 times more number of bytes as opposed to what your AlexNet had. And in terms of parameters, you see almost like 2.3 times more than AlexNet. And in terms of the operations, you see it's almost like 20 times bigger than the AlexNet. Okay, so 2014, it was not VGG that won the ImageNet. It was GoogleNet. But again, like we are comparing two different papers, and the thing that GoogleNet was able to come up with was the efficiency, because this was from Google. The whole point for them was to reduce the number of operations, reduce the number of memory, but still hold a good accuracy in ImageNet challenge, because they wanted to deploy it on devices and their clusters and stuff. So they wanted to reduce the number of computation and the memory it was costing them. Okay, so GoogleNet was focusing on efficiency. Again, there is a little bit of thing on their name. They were trying to give tribute to Jan LeCun's paper, so that's why it's called like LeeNet here. Okay, so yeah, like I said, they are trying to reduce the number of parameters, memory usage, and computation. And if you look at this network, the input is here. I know it's too small, and the output is on the top. So they kind of proposed two different things to the architecture. One is the STEM network, which is almost similar to what we saw in VGG16, but it downsamples the spatial resolution too fast than what we had earlier. So for instance, from going to 224 to 28, it uses like 124,000 parameters, whereas VGG was using 1.1 million parameters. So it's almost like cut down by a significant amount. So these are some of the types that GoogleNet was trying to do to actually improve the efficiency. Yeah, we are exactly comparing with what VGG was going to reduce from 224 to 28 in this case. The other cool thing that they kind of introduced was inception module. So you can see this is a different architecture, right? We are having parallel branches. And the reason being that VGG was giving you design choices saying instead of using 5x5 or 7x7, we could just use 2 layers of 3x3. Here, the design choice was basically like, why do we have to figure out like one particular convolutional like filter? You could maybe use them all in parallel. So you can see here, you have 1x1 convolution, 3x3, 5x5, and also max pooling. So it is trying to give a different set of design choices as opposed to what VGG was giving for the sake of efficiency. And they also call this like 1x1 convolution as bottleneck. We'll see that when we come to ResNet in the next lecture. Okay, so the other thing that was different from the previous architectures that came before GoogleNet was this global average pooling that happens towards the end. So they're trying to remove multiple fully connected layers with this global average pooling. So if you think about it, the average pooling here is basically taking an input of 1024 channels, let's say with H and W being 7x7. And they are doing the average pooling over the entire input spatial size, right? Because the kernel size for the average pooling is 7. So there's not too much shift happening, it's just one location. And you collapse that into a channel of 1024 with resolution 1. So it's a different operation as opposed to what you would commonly do with a fully connected layer. And this is followed by a fully connected layer where they're reducing 1024 into 1000 because 1000 is the number of classes in your ImageNet. This has been used later on because this, so if you remember the number of parameters that went into fully connected networks was super large. So this is one way to account for that. Like you can use this average pooling to reduce that number of parameters. So if you want to compare with VGG, so we were looking at large number of parameters here. So we can cut down that using this average pooling. Okay. So some things to remember from GoogleNet is that they also had auxiliary classifiers. So around that period of time, it was super hard to train neural networks if it is more than 10 layers. So they had to do like few hacks to actually make it work, especially the gradients kind of die out or do not propagate well in deep neural networks. So they had to use these auxiliary classifiers at different stages, which would give you different set of weights at that particular time. So you can imagine gradients flowing from here along with the gradients flowing from here. So you can also ask, like, the VGG also had about 19 layers. Did they do any hacks? So they did do hacks. Like what they did was, like, they had a smaller network or a shallow network that they trained, and then attached those weights or like introduced layers to those shallow network to actually make it 19 layers. So people had to do a lot of hacks to make their network train. And this is what GoogleNet did. So they had these auxiliary classifiers. And I think after this, like, having auxiliary loss term is kind of common feature in doing certain perceptual tasks. So I think that kind of came from this architecture. Okay. So yeah, so we don't have batch normalization till now. So this is all happening before batch normalization. So after this, I think the batch normalization made a huge impact. So you don't actually have to go through all of these hacks. Okay. We saw GoogleNet. And in 2015 comes ResNet. So you can see the huge jump in the number of layers. We went from 22 layers in GoogleNet to 152 layers. So it's like much deeper network. We will talk about that in the next lecture and see how much impact it has made in the deep learning architectures. Okay, so next time we'll talk about ResNet and also like training neural networks. And with that, we are at the end of today's lecture.